Welcome to the second lecture on sets. So, in the last class we talked about what are sets, and then we studied about some operations on sets and we introduced many notations. So, sets are very useful concepts which is used in almost every branch of mathematics. So, when you study about functions, relations, everywhere you will see that sets comes. So, it is very important to understand the concepts of sets well. So, let me start. So, first let me recall that we talked about two different ways of representing a set. One was roster form, and the second one is set builder form. In the roster form, let us recall that we list all the elements, all elements are listed. Note that in general for infinite sets, like the set of real numbers, it is not possible to use the roster form. So, we need set builder form. Though for some infinite sets, like if we have a set of natural numbers or even numbers, we can still use roster form as well, but set builder form in general is more useful. So, I will introduce some notations. So, we will define what are called intervals in the set of real numbers. So, let a and b are real numbers with a less than b, then we write the interval a b, this is equal to set of all x such that x is a real number and a is less than x is less than b. This is called open interval. So, this is set of all real numbers which are strictly between a and b, and we use this closed bracket a b. This will mean all x such that x is a real number and a is less than equal to x is less than equal to b. This is closed interval. And we also use half open or half closed intervals. So, a b, this will mean x such that x is a real number and x is strictly bigger than a and less than equal to b. Similarly, this will denote all x such that x is in R and a is less than equal to x is less than equal to is less than b. And we use some infinite intervals also. So, if I write a comma infinity, this will mean all x is that x is a real number and x is bigger than a. Closed a infinity will mean all x such that x is a real number and x is bigger than equal to a. Minus infinity to b, this means x says that x is less than b. Minus infinity to b closed, this will mean all x such that x is a real number and x is less than or equal to b, and we use minus infinity infinity to denote the set of all real numbers. Okay, so, infinity here is just a symbol and this gives you the intervals. These are all subsets of all these intervals are subsets of R. So, these interval will be very useful when you learn calculus or in other subjects. So, next we will also introduce. So, we defined what we mean by subsets of a set. So, we also sometimes see this term called proper subset. So, we say A is a proper subset of x if A is a subset of x, but A is not equal to x, right. And the notation we use is so for subset we use A subset of x, and for proper subset we write it like this. So, this will mean that A is a proper subset of x. This means that every element of A is in x and there is at least one element in x which is not in A. So, for example, one 2, this is a proper subset of the set 1 2 3. Another term used is superset. So, we say B is a superset of A if A is a subset of B. And the notation here is we use this to denote that B is a superset of A. And then if B is a superset of A, but B is not equal to A, we can say proper superset of A, B is a proper superset of A. If we write like this means this and B is not equal to A. Okay, in the last class we learnt about some operations on sets like union, intersection, complement and set difference. So, today we will list down some properties of these operations. Union and intersection. So, first one, if I have two sets, then A union B is same as B union A. This is called the commutative law. Second is, if I have three subsets, then A union B union C, this is same as A union with B union C. This is called the associative law. So, you must have heard these terms for addition of real numbers, that addition is commutative, addition is associative. So, similarly taking union, this is commutative, associative. Third is that we have this is empty set. So, if you take A union with empty set, that is equal to A. So, this is like for real number A plus 0 is equal to A, this is true, and A union A is equal to A. So, this sometime we call identity law, and this is called idempotent. And also I will write one more. So, if A is a subset of U, then A union with U is equal to U. And we have similar properties for intersection. So, again intersection is commutative, A intersection B is same as B intersection with A. A intersected with B intersected with C is equal to A intersected with B intersected C. A intersected with empty set gives empty set. A intersected A is A, and if A is a subset of B, then A intersected with B is same as A. So, these properties are easy to check. The next one important thing is what is called the distributive law. So, if we have 3 sets A, B and C, then A intersected with B union C is equal to A intersected with B union A intersected with C, right. So, this says that the intersection distributes over the union. So, this again analogous thing is that if you have product and sum, then A times B plus C is A times B plus A times C, and also A union with B intersected C, this is A union B intersected with A union C. So, this let me explain the first one by using Venn diagram. So, if we have A, B and C are 3 sets, then let me write A intersected with B is denoted by this red, and A intersected with C is this part, and if you take the union of these two, so red is A intersected with B and blue part is A intersected with C, and the union of these is exactly A intersected with B union C. Similarly, you can do for the second one. Another thing, some properties of complements. So, if I have U is a universal set, then A complement is nothing but U minus A, right. So, first property is that if we take complement of the complement, then we get equal to A, right. This is because A complement complement is equal to U minus A complement, and this is equal to U minus A, which is equal to A itself. and what is the complement of the empty set? Since empty set has no element, the complement will contain all the elements of U, and the complement of U is just the empty set. Another thing is that if A is a subset of B and both are subsets of the universal set U, then the complement of B is a subset of complement of A, right, because anything in B complement means that all those elements which are in U, but not in B. So, if an element is not in B, it cannot be in A. Right. So, x belonging to B complement, this implies x is not in B, which implies x is not in A, since A is a subset of B. If x was in A, then it has to be in B also. This implies that x is in A complement. So, next we will relate unions and intersection with complement. So, these are two very important properties, and these are called De Morgan's law. So, the first one is, if I take complement of the union, that is equal to the intersection of the complements. A union B complement is same as A complement intersected with B complement, and second one, if I take complement of the intersection, then I get union of the complements. Again, this one you can see by drawing diagram. So, if you draw Venn diagram, if you see A union B complement, this is everything which is not in A and it is not in B. So, this part is A union B complement. What about A complement and B complement? A complement is all the elements which are not in A. But it includes these points which are in B, but not in A. Similarly, B complement is all the elements which are not in B, but it can contain the elements which are in A, but not in B. Now, if you see the intersection of the elements which are common to these two red ones is exactly equal to the blue one. So, this is our A complement, this is our B complement, and then this is equal to A complement intersected with B complement. The next thing that we will do is, suppose we have two sets A and B and we know the number of elements in A and B, then can we say anything about the number of elements in the union? So, first let me write let A and B are two finite sets such that A intersection B is empty. That is, A and B are two disjoint sets, then in that case what is the number of elements in the union? So, n of A union B, this is equal to n of A plus n of B, right, because the number of elements in the union, anything in the union means that it is either in A or in B, and the number of elements in A is n of A, this is number of elements in B is n of B, this is number of elements in A, and because there is no element which is common to both A and B, this is clear that the number of elements in the union is sum of the number of elements in A and B. So, in this case we have two sets A and B which are disjoint. So, counting the number of elements which are in either A or B is same as just adding the number of elements in A and number of elements in B. Next we will see that what can we say in general. So, in general n of A union B, this is equal to n of A plus n of B minus n of A intersection B. This is a very important formula for the number of elements of the union, which you will find very useful when learning probability. So, let us prove why this is true. So, proof, we can write the union A union B as the disjoint union of A minus B union with A intersection B union with B minus A, right. So, A union B can be broken into these three parts. And these are disjoint, where A minus B, A intersection B and B minus A are pairwise disjoint. Now, we know that for disjoint sets the number of elements in the union is sum of the number of elements in each of them. So, therefore, n of A union B is equal to n of A minus B plus n of A intersection B plus n of B minus A. Now, we want to express this in terms of the number of elements in A and B. So, note that the number of elements in A is nothing but the number of elements in A minus B and plus number of elements in A intersection B. So, this is equal to n of A minus B plus n of A intersection B plus n of B minus A plus n of A intersection B and minus n of A intersection B. So, but A is equal to A minus B union A intersection B, this is disjoint union. So, n of A is equal to n of A minus B plus n of A intersection B. Similarly, n of B is n of B minus A plus n of A intersection B. So, if you see the previous page, the first two terms n of A minus B plus n of A intersection B, this is n of A, n of B minus A plus n of A intersection B, this is n of B, and then we have minus n of A intersection B. So, therefore, n of A union B is equal to n of A plus n of B minus n of A intersection B. So, this is very important formula. So, here we have to subtract the number of elements in the intersection, because when we are counting the number of elements of A and number of elements of B, the elements in the intersection are counted twice. So, we need to subtract. So, that is one way that you can remember this formula. Now, what about n of A union B union C? Suppose I have 3 sets, then can we write similar formula for the number of elements in the union of A, B and C. So, n of A union B union C, this by the previous formula we can write as n of A plus n of B union C minus n of A intersected with B union C. And n of B union C, we know again that this we can write as n of B plus n of C minus n of B intersection C minus n of A intersection B union C. Now, by De Morgan's law, by the distributive property, A intersection B union C, this is equal to A intersection B union A intersected with C. So, n of A intersected with B union C, this is equal to n of A intersected with B plus n of A intersected with C minus n of the intersection of the two sets, which is A intersected B intersected with A intersection C. So, this is equal to n of A intersection B plus n of A intersected with C minus A intersection B intersection with A intersection C is nothing but A intersected with B intersected with C. So, we had this equation and then we have equation 2. So, if you put the value of n of A intersection B union C from equation 2 in equation 1, what do we get? N of A union B union C, this is equal to n of A plus n of B plus n of C minus n of A intersection B minus n of A B intersection C minus n of A intersection C plus n of A intersection B intersection C. Right. So, for the union of 3 sets, the number of elements, you first add the number of elements in each of them, n of A plus n of B plus n of C, then you take the intersection 2 at a time and then you subtract the number of elements in them, and then you look at the intersection of all 3, then you will have to add them. So, here when you subtract the number of elements in the intersection of 2 at a time, then you have subtracted the number of elements in the intersection. So, you will have to add that to get the number of elements in the union of 3. Similarly, one can derive formula for the number of elements in union of 4 also, but we will not do that. So, let us look at an example. So, suppose there are 400 people and they speak either English or Hindi, or there are some people who speak both. And what we know is that 250 people they speak Hindi out of these 400 people, and out of this 400, 200 people they speak English. Then what we want is that how many speak both languages. Okay, so what we have to do, so let H, this is the set of people speaking Hindi, E is the set of people speaking English, So, what is given is n of h is 250, n of E is 200 and n of H union E. So, H union E is the set of people who speak either Hindi or English. This is given to be 400. And what do we want to find? What is n of H intersected with E? How many people are who speak both Hindi and English? So, we know that this we can calculate by using this formula. N of H union E is equal to n of H plus n of E minus n of H intersection E. So, this implies n of H intersected with E is equal to n of H union E minus this plus n of H plus n of E. So, this is equal to minus 400 plus 250 plus 200, which gives 50. So, there are 50 people who speak both Hindi and English. Okay, so, let me do some problems. Suppose we have sets A, B and C such that A union B is equal to A union C and A intersected with B is equal to A intersected with C. You are given that A union B is equal to A union C and A intersected with B is A intersected with C. Prove that B is equal to C. So, let me show how to prove that two sets are same. So, to show that B is equal to C, what we will prove is that B is a subset of C. So, to show B equal to C, it is enough to show that B is a subset of C and C is a subset of B. So, let us see why B is a subset of C. So, let X be any element in B. We have to show that X is also in C. So, we know that B is a subset of A union B. So, if X is in B, it is also in A union B, but A union B is equal to A union C. So, this implies that if I take X in B, X belongs to the union of A and C. So, this implies X belongs to A or X belongs to C. Now, what we have to prove is that X is in C. So, if X is in C, then we are done. X is in C, then okay. If otherwise, if X is in A, then x belongs to A intersected with B, because x was already taken to be in B. But A intersected with B is equal to A intersected with C. So, x belongs to A intersected with C. This implies that x is in C. So, in both cases we have x belonging to B implies x belongs to C. Therefore, B is a subset of C. And similarly, you can show that C is a subset of B. If you take any x in C, then by the same argument you show that it also belongs to B. This implies that B is equal to C. Okay, second problem, let me do this. So, we will show that if the power set of A is equal to power set of B, then A is equal to B. So, let me recall that power set of A, power set of A is equal to set of all subsets of A. So, this is equal to all C such that C is a subset of A. So, if we know that the power sets of two sets are same, we want to prove that the sets are same. So, we want to prove that A is equal to B. So, note that since A is a subset of A belongs to power set of A, right. Power set contains all subsets. So, in particular it contains A also, but power set of A is given to be equal to power set of B. So, this implies A belongs to power set of B, which implies that A has to be a subset of B. Right. And similarly, power set of B is equal to power set of A. So, B belongs to power set of B, which is equal to power set of A. This implies that B is a subset of A. Hence, A is equal to B. So, let me introduce some notations which we have been using. So, if I write some statement 1 implies statement 2, this means if statement 1 is true, then statement 2 is true, right. So, instead of writing this if then statement, we use this implication sign to say that statement 1, if statement 1 is true, then statement 2 is true, and another one we use statement 1, this both sides implication, statement 2, this means statement 1 is true if and only if statement 2 is true. So, that means that if statement 1 is true, then statement 2 has to be true, and also if statement 2 is true, then statement 1 is true. And there is also a shortcut notation to write if and only if. We write I double F, this means if and only if. So, instead of this double implication, we sometime write I double F to mean this. Okay, let me give one more example. So, suppose A intersected B is non-empty, B intersected with C is non-empty, and A intersected C, this is also non-empty. Is it true that A intersected B intersected C is non-empty? So, if we have 3 sets such that pairwise they are not disjoint, we have something in common, then is it true that there is something common in each of them? So, the answer is no, because let us take this example. Let A is equal to set containing only 2 points 0 and 1, B is equal to 1 and 2, and C is 0 and 2. Right. So, 0 belongs to A intersection C, 1 belongs to A intersection B, and 2 belongs to B intersection C. So, all these pairwise they are not disjoint, but is there any element which is common to A, B and C? 0 is not in B, 1 is in A and B, but not in C, 2 is in B and C, but not in A. So, A intersection B intersection C, this is empty. Okay, so we will stop here today, and in the next class I will do some more examples of sets, and that will finish the chapter on sets. Thank you.